Hello students, so today in this video I will explain what is electric dipole and how can we derive the expressions for electric field due to an electric dipole on its axial and equatorial positions. So let us start with the definition of the electric dipole. So what is electric dipole? What is electric dipole? So electric dipole is a system of two equal and opposite charges. System of two equal and opposite charges separated by a small distance. So how much it will be this small distance? Usually this can be small like atomic distances in molecules, or it can be maximum in millimeters order, or sometimes in centimeter you can see in questions, but not very large than that. Okay, so electric dipole is a system of two equal and opposite charges. Suppose we have a charge minus q and a charge plus q. So both of these charges have same magnitude small q and they are separated by a small distance. So suppose we call that distance between these two charges as 2L. Why are we taking this 2L? This 2L doesn't mean that you have to multiply the distance given between these two charges by 2. Whatever distance has been given, that total distance you will take as 2L. So basically the total distance is the 2L. So you don't need to multiply the given distance by 2. So remember this point. And why are we taking this 2L? Because our coming further calculations will become easier with this 2L distance of the dipole. Anyway, so let's move forward. So this is an electric dipole with minus q and plus q charges which are separated by a small distance 2L, and there is a characteristic quantity which defines the construction and the strength of this electric dipole, so that we call electric dipole moment. What is this electric dipole moment? So electric dipole moment is a characteristic of the electric dipole. It is defined as the either charge and distance between charges. So this is basically product of these two, product of either charge and distance between the two charges. So this is usually represented by a small letter p or lowercase p, and this is, as I have written, is it equal to product of either charge, which is same for both the charges, magnitude is small q, multiplied by the distance between these two charges that we have taken 2L. So the dipole moment will be defined as p equal to q times 2L. And one very important thing is that this is a vector quantity. So every vector quantity has a direction. So what is the direction of this electric dipole moment? So its direction is opposite to the direction of electric field, because electric field direction for electric dipole or any system of charges, as you have studied, that is always directed from plus q to minus q charge. Electric field lines always originate from positive charge and they terminate at the negative charge, but electric dipole moment direction is contrary, opposite to that. So for this dipole I have drawn in the diagram, the electric field for this will be from plus q to minus q charge. Like this you will draw from plus q to minus q. Okay, but the dipole moment direction will be opposite to this. So the electric field is directed from plus q to minus q, but electric dipole moment will be opposite to this, from minus q to plus q. So direction of electric dipole moment is always from minus q charge to plus q charge. This is important to remember, and it is a physical quantity, so it will definitely have a unit also. So what is the SI unit of this electric dipole moment? As you can see the formula, it is charge times the separation between charges. So SI unit will be the unit of charge, which is coulomb, times unit of separation or distance, that is meter. So coulomb into meter, that is the SI unit of electric dipole moment. And if you want to write the dimensional formula for this, So dimensional formula for charge, that is ampere times second or ampere into time. So it will be ampere into time is the dimensional formula for charge into L for distance. So you can write it as LTA. That will be the dimensional formula for electric dipole moment. Okay, so this was all about electric dipole, and now we will calculate electric field due to this electric dipole at two specific positions, which we call axial position and equatorial position. So let's start. Suppose we have okay, let me write it first. So we are going to find electric field due to an electric dipole. And there will be two specific points at which we will find the electric field. So first is electric field due to an electric dipole at axial position, or sometimes we also call it end-on position, or one more name is there for this position that we call longitudinal position. Okay. So we are going to find the expression for electric field due to an electric dipole at its axial position. What is axial position? So the line joining the two charges in the dipole, that is known as axis of dipole. So suppose this is our dipole, minus q charge, this is your plus q charge. Then the line joining these two charges, that we call axis of the dipole. So this line is the axis of the dipole, and any position on this line or any point present on this line, that we will call a point on the axis. So suppose this is point P, which is at distance small r from the center of the dipole, and we take total separation between the two charges is 2L. So we can divide that 2L as L from center of the dipole is minus q charge is at L distance, and plus q charge is also at L distance. So this is L and this is L. Okay, so the distance of this point P at which we are interested in finding the electric field strength. So that point distance from this plus q charge, that will be this total is R, this is L, so this will be R minus L. And similarly the distance of this point P from minus q charge, that will be this R plus L, so that total will become R plus L. Okay. Yeah, so now net electric field at point P. So at point P there will be two electric fields due to the two charges present here, minus q and plus q. The electric field at point P due to plus q charge, that will be, suppose I say that is E1, and of course that will be away from positive charge, and it will have slightly larger magnitude as compared to the electric field caused by minus q charge, because minus q charge is little farther from point P as compared to plus q. So suppose electric field due to minus q charge, that we call that is E2. So E2 will be directed towards the minus q charge, because electric field is always towards the negative charge and away from the positive charge. So E1 will be towards the right and E2 will be towards the left, and also the magnitude of E1 will be slightly larger than the magnitude of E2, because the charge plus q is closer to point P as compared to the charge minus q. Okay, so the two electric fields E1 and E2 are in opposite direction. So the net electric field at point P, net electric field at point P, what we will write it, E equal to E1 minus E2. We are basically writing the larger magnitude electric field is E1 minus smaller magnitude electric field E2, and E1 is larger, so net electric field will be directed towards the direction of E1. So this is the direction of net electric field, and if you notice, the net electric field will be parallel to the direction of the dipole moment for this system, because dipole moment will also be directed from minus q to plus q, and we can see that the net electric field E is parallel to the net electric dipole moment. So we will write the direction of this net electric field as parallel to the dipole moment. Anyway, so let's write is the magnitude of E1 and E2. We will use Coulomb's law basically to determine the electric field due to a point charge, and if you remember, that is given as 1 upon 4 pi epsilon naught q divided by separation square or distance square. So electric field E1 due to plus q charge, that will be written as 1 upon 4 pi epsilon naught charge q divided by distance square, which is r minus l whole square, minus 1 upon 4 pi epsilon naught electric field due to charge minus q, that will be 1 upon 4 pi epsilon naught q divided by r plus l whole square, right? Now let's simplify this. E is equal to, take the common terms outside, so it will be q upon 4 pi epsilon naught, and it will be 1 upon r minus l whole square minus 1 upon r plus l whole square. Okay, so now this will become q divided by 4 pi epsilon naught. Take these two terms LCM, so r minus l whole square, r plus l whole square. It can be written as r minus l, r plus l whole square, and in numerator here it will become r plus l whole square minus r minus l whole square. So this is q divided by 4 pi epsilon naught, this is 4, and here in denominator this is r minus l, r plus l, it will become r square minus l square and whole square, and if you open this r plus l whole square, it will be r square plus l square plus 2rl, and minus r minus l whole square, if you will open that, you will get r square plus l square minus 2rl, but there is a minus sign outside, so it will reverse all the signs, so it will become minus r square minus l square plus 2rl. Now this minus r square minus l square will get cancelled with this plus r square plus l square, and what will be left? Q divided by 4 pi epsilon naught, and this will be 2rl plus 2rl, that will be 4 times rl divided by r square minus l square whole square. I can cancel this 4 in numerator and denominator, but I am not going to cancel that because I am going to readjust the terms. So what I can write it now, 1 upon 4 pi epsilon naught, and you can split this 4 into 2 parts, 2 into 2, so 1 2 is outside, another you can write q times, another 2 will be written with l, so it will be q into 2l, and one r is also there, this divided by r square minus l square whole square. And I hope you would have understood why I have written the numerator like this, because this q into 2l, I am going to write that as this term as the dipole moment. So this will now become 1 upon 4 pi epsilon naught 2 p r divided by r square minus l square whole square. So this is the expression for net electric field due to an electric dipole on its axial position. And very important thing, don't forget to write this, direction of this electric field is parallel to dipole moment P. What is P? P is dipole moment. And we can also take a special case here. You can take a special case. What is a special case? Suppose the distance is small, r is much greater than l. Means the dipole is very small or the point is very far from the dipole. If r is much greater than l, then r square minus l square will almost be equal to r square, because l square is so small as compared to r that can be neglected. So now electric field E will become 1 upon 4 pi epsilon naught, and it will be 2 p r divided by l square has been neglected, so it is r square whole square, then again r to the power 4 it will become, and if you cancel one r in numerator and denominator, what you will get? You will get 1 upon 4 pi epsilon naught 2p divided by r cube. So this is very important result. You should remember electric field due to electric dipole. For far away points, the electric field is inversely proportional to distance q, r cube, inversely proportional. So if you remember, electric field due to point charge is inversely proportional to r square, but for an electric dipole, it is inversely proportional to r cube. Okay, that's all for axial position. Now we will come to equatorial position. So next topic is electric field due to an electric dipole at equatorial position, or this position is also called broadside on position, or there is one more name for it that we call transverse position. So now we are going to find the electric field expression due to an electric dipole on its transverse position. So suppose again we have an electric dipole, similar electric dipole as we had in the previous case. This is minus q charge, this is plus q charge. Now what is this equatorial position? The perpendicular bisector of the axis of the dipole. So this is the axial position, and a perpendicular bisector means a line passing through the center of the dipole but perpendicular to this. So you can understand that in 3 dimension there can be infinite number of such lines, right? You can rotate this line in 3 dimension and you will get a whole plane, and that plane will be called equatorial plane. So there is not only one equatorial line, rather there are infinite number of equatorial lines, and they all together make the equatorial plane. And any point lying on this equatorial position, equatorial plane, any point that will be termed as point on equatorial position. And now we are interested in finding the electric field strength at this equatorial position. So suppose the distance of this point P from the center of the dipole is small r, and it is like before, minus q charge is at distance L from center of the dipole, and plus q charge is also at distance L from the center of the dipole. Now again there will be 2 electric fields at point P due to these 2 charges. So suppose I say electric field due to plus q charge at point P, that will be E1, and electric field due to minus q charge, that will be E2. And interestingly, both of these 2 electric fields will have same magnitude because point P is at equal distances from these 2 charges, but their directions will be different. The electric field E1 will be away from plus q charge and E2 will be towards the minus q charge. And let's draw a line parallel to the axis of the dipole, and suppose if this angle is theta, then of course this angle will also be theta, and if this is theta, this will also be theta because this is perpendicular bisector line. These 2 line side lengths will be equal, so angles will also be equal, and if this is theta, this will also be theta. Now magnitude of E1 and E2 both will be same, not their directions but magnitudes will be equal, and this distance is L, this distance is R. So any of these 2 distances, they will be using the Pythagoras theorem, they will be under root R square plus L square. This also, and this distance also will be equal to under root R square plus L square. So magnitude of either E1 or E2 using the Coulomb's law or formula for electric field due to point charge, that will be 1 upon 4 pi epsilon naught charge q divided by distance square, means distance is square root of R square plus L square whole square. It will be 1 divided by 4 pi epsilon naught q divided by R square plus L square. This is the magnitude of both the electric fields. So E1 and E2 are equal in magnitude, so you can resolve these 2 electric fields in perpendicular and parallel components. So E1 can be resolved like this. It will be E1 sine theta, and E1 cos component will come in this direction, E1 cos theta. Similarly, you can divide this E2 also into components. E2 sine theta will come in this direction, and E2 cos theta will again be parallel to E1 cos theta. And as E1 and E2 are magnitude wise equal, so E1 sine theta, E2 sine theta will also be equal, so they will cancel each other, and the parallel components E1 cos theta and E2 cos theta being in the same direction, they will be added together to produce the resultant net electric field. So if E1 sine theta and E2 sine theta will cancel each other as they are equal in magnitude but opposite in direction. Okay, so E1 sine theta, E2 sine theta, they will cancel, and net electric field, now net electric field at point P, that will be E equals E1 cos theta plus E2 cos theta. And if we put the values of E1 and E2, what we have calculated just above, this one, so 1 upon 4 pi epsilon naught q upon r square plus l square, so it will be q divided by 4 pi epsilon naught r square plus l square, and cos theta can be taken common, plus E2 is also the same, q upon 4 pi epsilon naught r square plus l square, and this whole thing multiplied by cos theta, and you can write this as 2 times either value, so it is twice of this, so it will be 1 upon 4 pi epsilon naught 2q divided by r square plus, is the same thing, I have written twice of this first term, into cos theta. From the diagram you can write that cos theta can be written as base, this base upon hypotenuse, so base is L divided by hypotenuse under root L square plus R square, so it will be L divided by square root of R square plus L square, and you can rearrange the terms further to give you 1 upon 4 pi epsilon naught. The numerator can be written like q times 2L, and this whole thing divided by R square plus L square, and the term is square root of R square plus L square, and square root means power 1 by 2, so this is R square plus L square power 1, then another term R square plus L square power 1 by 2, and those two powers will be added together, and you can write it, this whole thing, as R square plus L square power 3 by 2, and as you remember, this q into 2L, that is the dipole moment, so you can write it as 1 upon 4 pi epsilon naught p divided by r square plus L square power 3 by 2. So this is the net electric field at equatorial position, and what will be the direction? If you see here, the electric dipole moment, as I told before, that will be directed from minus q to plus q charge, so this is the direction of electric dipole moment, but you see that net electric field is directed in this direction, E1 cos theta plus E2 cos theta, so that is this net electric field, and p vectors are opposite in direction, so you will write that the direction of this electric field is opposite to dipole moment p. So electric field at axial position is parallel to dipole moment, while electric field at equatorial position is opposite to the dipole moment. We can also take the special case here like before. So special case, suppose we say that if distance small r is much greater than L. So if small r is much greater than L, means the point is very far from the dipole, or the dipole is very small in length, then r square plus L square will almost be equal to r square, because L square is so small, adding it to r square will not make any change, r square will remain almost same, so you can write it as E is equal to 1 upon 4 pi epsilon naught p divided by r square power 3 by 2, so this 2 will get cancelled, and net electric field you will be left with the expression 1 upon 4 pi epsilon naught p divided by r cube. So again you notice that net electric field is inversely proportional to r cube for equatorial positions also. And one more thing you should remember here, at axial position, suppose I say this value, special case value, I write it as EA, A means axial, and this value as EE, E means equatorial. So if you compare axial and equatorial positions, axial value was 1 upon 4 pi epsilon naught 2p upon r cube, this value 1 upon 4 pi epsilon naught 2p upon r cube, but this value is 1 upon 4 pi epsilon naught p upon r cube. So you get, comparing these two, so comparing these two, you get axial position value is twice of equatorial position. This means that if you are at larger distance from the center of the dipole, or if the dipole is very small, then at the same distance on axial position, the electric field will be double of the value of the electric field which is obtained at the same distance on equatorial position. Okay, I hope the message was clear and you learned how to derive the expressions for electric field at axial and equatorial positions, and what is electric field, what is electric dipole moment. I tried to explain it all to you. So you can comment and tell me how did you like this video, and if you have any doubt, any question, you can post it in comments and I will try my best to answer those questions. So thank you very much. Take care and bye bye. Keep watching my videos and share it with your friends also if you are liking them. Okay, thank you. Bye bye.